Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 27th, 2026, just 4 days ago. It introduces an online generative enhancer that transforms imperfect neural renderings into photorealistic video, with over 84% of users preferring its output over the next best method. The paper is titled DiffusionHarmonizer, Bridging Neural Reconstruction and Photorealistic Simulation with Online Diffusion Enhancer. And as we'll see later, this approach offers a scalable way to train autonomous robots using highly realistic synthetic data. So Figure 1 illustrates exactly what this enhancement looks like in practice. The top row demonstrates object insertion. Specifically, look at the bright red car on the left. In the raw input, it clearly looks pasted on, lacking proper lighting interactions. However, the enhancement result next to it fixes this, adding realistic shadows and reflections to harmonize the object with the environment. Below that, the video comparison shows how the method handles general scene artifacts. While the input frames in the middle row suffer from blurry distortion in the sky, the enhanced outputs in the bottom row are crisp and photorealistic. Well, Figure 1 showed the results, but Figure 2 explains the system behind them. The top panel details the data curation pipeline, which generates synthetic training pairs, since real-world ground truth is unavailable. It systematically simulates 5 factors: ISP modification, relighting, PBR shadow simulation, asset reinsertion, and artifact correction. Then, the bottom panel shows the runtime model. It uses the current frame, plus a short history of previous frames to ensure temporal consistency, feeding into the yellow single-step backbone to generate the enhanced video. Alright, moving to the results. Figure 3 compares the model against state-of-the-art baselines on out-of-domain testing data. The top row in the upper section shows the raw simulation input, which often lacks realistic lighting. In the second row, the proposed method successfully harmonizes these scenes, adding plausible shadows and correcting tones without altering the underlying geometry. In contrast, the lower rows display baselines like SD-Edit and WAN Video. These approaches tend to over-edit the image, introducing hallucinations or drastically changing the color palette, which breaks the structural fidelity needed for reliable simulation. So, Figure 3 gave us the visual proof, but Table 1 now backs that up with hard numbers. The second column highlights a critical advantage: inference speed. The proposed model runs at 212 milliseconds, which is over 10 times faster than the video diffusion baseline, WAN Video v2 versus. Yet, looking at the metrics on the right, it still achieves the lowest FID and F versus D scores, indicating superior realism. Crucially, the high dyno structure scores confirm that it preserves the underlying scene geometry much better than standard editing models. Well, while Table 1 established the metrics, Figure 5 visually breaks down why the specific loss function matters so much. The top left panel shows the raw input, which is noisy and indistinct. If we look at the top right, training without perceptual supervision creates an oversmoothed, blurry result. Using a standard LPIPS loss in the bottom left sharpens it but introduces distracting high-frequency artifacts. In contrast, the bottom right demonstrates that the proposed multi-scale perceptual loss achieves the best balance, removing noise while keeping the textures crisp. So, while the previous figure focused on the loss function, Table 6 investigates the data itself. It quantifies how much each part of the synthetic data pipeline matters. The first column shows the full model achieving the lowest scores for both FID and F versus D, representing the best performance. Moving right, we see that leaving out components like ISP modification or shadow simulation consistently degrades quality. Notably, the last column reveals that removing artifact correction causes the largest error spike, confirming that this data source is essential for the model to learn how to repair broken renderings. Alright. While the previous tables focused on technical scores, Table 4 asks the ultimate question: does it actually look better to humans? The results in the first row are striking. Against powerful baselines like SD-Edit and WAN Video v2 versus, human evaluators preferred the proposed method overwhelmingly, choosing it between 84 and 90% of the time. The second row shows that versus LM evaluators agree, favoring the new approach by similarly wide margins, which confirms that the visual improvements are distinct enough to be recognized by both people and automated systems. Wrapping up, 2 key takeaways stand out. First, DiffusionHarmonizer effectively bridges the gap between neural reconstruction and photorealism using a highly efficient single-step model. Second, the success of its synthetic data pipeline proves we can train robust enhancers even without real-world ground truth, unlocking scalable, high-fidelity simulation for robotics. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.